Throughout history, humanity has been captivated by the idea of immortality. From the eternal youth sought in myths and legends to the modern scientific quests to extend human life, the concept of living forever has always intrigued us. But if we turn our gaze to the vast universe, can anything within it claim true immortality? Today, we're embarking on a cosmic journey to explore this question deeply. We'll delve into the lifespans of the smallest particles known to man, the majestic life cycle of stars, the mysterious endurance of black holes, and the grand scale of the universe itself. While it might seem that some entities in the cosmos endure for an almost infinite amount of time, the reality is more complex. This video will explore whether anything in the universe can truly be considered immortal. Let's delve into the science behind the impermanence of all things cosmic. Concept of immortality. Immortality has fascinated humans for as long as history itself. In ancient myths, gods and immortals live beyond the constraints of time and death, reflecting humanity's deep desire to transcend its mortality. Philosophers from Plato to Nietzsche have pondered immortality, often viewing it as a metaphor for the enduring impact of our actions and ideas rather than literal endless life. This quest for everlasting life not only shapes our beliefs, but also drives our innovations and stories, persisting as a fundamental aspect of human culture. In the realm of science, immortality takes on a more tangible but equally elusive definition. Scientifically, immortality would mean an object or system that exists unchanged without decay indefinitely. However, according to the laws of physics, particularly the second law of thermodynamics, everything in our universe is subject to entropy. This means that all matter and energy are in a constant state of decay and transformation, making true immortality impossible. Let's dive deeper into how this scientific perspective plays out across different scales in the cosmos. The transience of the microscopic. Subatomic particles. Zooming in on the microscopic scale, we encounter subatomic particles, which seem to straddle the line between mortality and immortality. Protons, for example, are incredibly stable and are predicted to have a lifespan exceeding the age of our universe by many orders of magnitude. Yet, according to theories in particle physics, even protons are not exempt from decay. Predicted by grand unification theories, proton decay, although not yet observed, would signify that even the most stable constituents of matter are not truly immortal, but are instead bound by eventual transformation and decay. Quantum theory. Quantum mechanics further complicates our understanding of stability at the subatomic level. This field of physics introduces principles like uncertainty and quantum tunneling, where particles behave in probabilistic rather than deterministic ways. These phenomena suggest that even on the smallest scales, stability is not absolute but is influenced by a myriad of factors at play in the quantum realm. This reinforces the idea that in the universe, change is the only constant, and absolute stability, or immortality, is a concept that doesn't hold up under the quantum microscope. The life cycles of stars. Birth of stars. Stars begin their life in stellar nurseries, regions rich with dust and gas called nebulae. Under the right conditions, these clouds of gas and dust start to collapse under their own gravity, forming clumps called protostars. As a protostar gathers more mass, its core heats up until it reaches the critical temperature necessary for nuclear fusion. This marks the birth of a new star, igniting it into a brilliant furnace that will shine for millions to billions of years, depending on its mass. Main sequence and death. Once a star enters the main sequence phase of its life cycle, it spends most of its life fusing hydrogen into helium in its core, releasing immense energy that powers the star's glow. A star like our Sun will remain in this stable phase for about 10 billion years. However, as it exhausts its hydrogen fuel, the star undergoes dramatic changes. For medium-sized stars like the Sun, this involves expanding into a red giant, shedding outer layers, and finally settling down as a white dwarf, a small, dense remnant that slowly cools over time. More massive stars may end their lives in a more spectacular fashion, exploding as supernovae and leaving behind either a neutron star or black hole. These endpoints mark the ultimate death of stars, indicating that even these colossal and long-lived celestial bodies are not immortal but are subject to life cycles and eventual decay. The longevity of black holes, neutron stars, and white dwarfs. Black holes. Formation and growth. Black holes are among the most mysterious and fascinating objects in the cosmos. They form from the remnants of massive stars that undergo a supernova explosion and collapse under their own gravity. This collapse is so severe that it creates a point in space where the gravitational pull is so strong that nothing, not even light, can escape. Longevity. Once formed, black holes can theoretically last for an astronomical amount of time. They lose mass extremely slowly through a process known as Hawking radiation, which is predicted by quantum theory but has yet to be observed. The evaporation rate is so slow that for a black hole of stellar mass, the time it would take to completely evaporate can exceed the current age of the universe by many orders of magnitude. Essentially, black holes could be the last surviving structures in a far future, dilapidated universe. Neutron stars. Formation and characteristics. Neutron stars are the compressed cores left behind after a massive star explodes in a supernova. They are incredibly dense, with the mass of the Sun packed into a sphere just about 20 kilometers across. This extreme density means that a single teaspoon of neutron star material would weigh billions of tons on Earth. Lifespan and cooling. Neutron stars begin their existence extremely hot and gradually cool over time by radiating away their thermal energy. While they cool and fade, their magnetic fields also decay, and their rotation rates decrease. However, neutron stars have incredibly long lifespans, enduring for billions of years. They are not truly immortal, though, as they continue to lose energy and eventually might become too cold and faint to be detectable. White dwarfs. Formation and cooling. White dwarfs are the remnants of medium-sized stars like our Sun. After exhausting their nuclear fuel, these stars shed their outer layers and leave behind a hot core that contracts into a white dwarf. Composed mostly of electron-degenerate matter, white dwarfs pack about the Sun's mass into a planet-sized object. Cooling and fate. White dwarfs emit no light or heat of their own but shine due to residual thermal energy. Over time, they cool and fade, transitioning from white to blue, then red, and finally black as they cool off completely. This process can take many billions of years, possibly up to tens of billions, depending on the star's residual heat and the physical conditions surrounding it. Theoretical models suggest that white dwarfs will eventually cool to become black dwarfs, a theoretical state of a cold, dark remnant emitting no detectable radiation. Each of these cosmic remnants tells a story of cosmic endurance and eventual decay. Black holes may be the longest-lived, potentially outlasting all other stellar remnants, while neutron stars and white dwarfs slowly radiate away their energy, gradually fading into the cosmic background. Despite their longevity, none can escape the ultimate fate dictated by the laws of physics, confirming that in the universe, nothing is truly immortal. Galactic evolution and decay. Formation of galaxies. Galaxies, vast islands of stars held together by gravity, are among the most significant and stunning structures in the universe. They form from immense clouds of gas and dust that, under gravitational pull, begin to condense and fragment into smaller clumps. These clumps eventually form stars and star clusters, which collectively evolve into fully fledged galaxies. Over billions of years, these galaxies continue to grow and evolve by accreting more gas, merging with other galaxies and transforming through internal processes like star formation and supernova explosions. Interactions and fate. Galactic mergers. One of the most dramatic aspects of galactic evolution is the merger process. Galaxies are not static entities. They move and interact gravitationally with each other. When galaxies pass close enough to each other, they can begin a complex dance driven by mutual gravitational attraction. Over time, this interaction can lead to galaxies merging to form larger, often elliptical galaxies. These mergers are cataclysmic events that trigger new waves of star formation as clouds of gas are compressed and destabilized. Future of galaxies. As galaxies age, their dynamics change significantly. Star formation gradually slows as the available gas is consumed or expelled by stellar winds and supernovae. This leads to an aging population of stars, and the galaxy's light shifts from the bright blue of young stars to the redder light of older stars. Eventually, as star formation ceases and existing stars continue to evolve and die, galaxies will lose their luminosity and become increasingly diffuse. Cosmic dissipation. In the far future, the fate of galaxies will be influenced by the expansion of the universe. As the universe expands, galaxies that are not bound by gravity to a local group or supercluster will recede from each other at increasing speeds. This cosmic redshift stretches the light from galaxies, shifting it towards the red end of the spectrum and beyond, eventually making them invisible to traditional observational means. This process, coupled with the cease of starlight, leads to a scenario where galaxies, as luminous entities, dissipate in terms of detectable light, fading into the dark backdrop of an expanding universe. The life cycle of galaxies showcases a complex journey from their vibrant youth, marked by intense star formation and dynamic interactions, to a quiet, fading existence in an ever-expanding universe. While they are not immortal, Galaxies undergo transformations that span billions of years, reflecting the ever-changing nature of the cosmos itself. Cosmic scale events and theories. Heat death. The concept of the heat death of the universe is based on the second law of thermodynamics, which states that entropy, or the measure of disorder, must increase over time. In cosmic terms, this means that eventually all energy will be uniformly distributed across the universe, leading to a state where no more work can be done and all processes cease, effectively freezing the universe in a state of eternal stillness. Big Freeze. Building on the idea of heat death, the Big Freeze focuses specifically on the continual expansion of the universe. As the universe expands, it also cools because the energy density decreases. Over time, this cooling will snuff out the stars one by one until the universe goes dark. As galaxies drift further apart and star formation halts, the universe will quietly transition into a vast, cold void. Big Rip. Contrasting with the gradual quiet of the Big Freeze, the Big Rip presents a more violent end scenario. This theory depends on the nature of dark energy potentially increasing in strength. If this force grows too strong, it could tear apart everything from galaxy clusters to individual atoms. Imagine the universe not fading into a whisper, but ending in a catastrophic tear as every structure is forcibly pulled apart in the final moments of cosmic time. Exploring these theories not only stretches our imagination, but also deepens our understanding of the universe's potential destinies. Each scenario presents a unique set of outcomes based on how fundamental forces might ultimately shape the cosmos's trajectory. Reflection on human and cosmic timescales. As we've ventured through discussions of the universe's potential fates, it's striking to juxtapose these cosmic events with the human perception of time. Our lifespans, typically spanning just a few decades, are but a blink when measured against cosmic timescales. The universe operates on a scale of billions of years. Stars are born, live, and die over periods that far exceed the entire history of human civilization. In this vast cosmic timeline, even phenomena that seem permanent to us, like the Earth or the Sun, are transient, subject to the same cycles of birth and decay as everything else in the cosmos. This realization brings us face to face with the philosophical implications of our quest for immortality. If everything in the universe, every star, every galaxy, even potentially the universe itself, is not immortal, what does that say about our own pursuits of everlasting life? Reflecting on these enormous time scales and the inevitability of change and decay might seem daunting, yet it also offers a unique perspective on our place in the universe. It challenges us to find meaning and purpose in a temporary existence, and perhaps to redefine what immortality means in a universe where everything changes. In our exploration of the cosmos and the concept of immortality, we've traversed from the microscale of subatomic particles to the vast expanses of galaxies and the theoretical endpoints of the universe itself. We've seen that everything from the smallest proton to the largest black hole is subject to the fundamental laws of physics, which dictate change, decay, and transformation. This journey highlights a profound truth. Nothing in the universe is truly immortal. Even entities that persist for billions of years are part of a grand cycle of birth, life, and eventual decay. As we reflect on these cosmic timelines, it puts into perspective our own fleeting presence and the temporal nature of all we hold dear. Yet this should not be a cause for despair, but rather a call to cherish the transient beauty of existence, to make the most of our brief moment in the sun, and to leave a lasting impact that echoes beyond our physical presence. In the end, perhaps our ideas, our actions, and the memories we create are the closest things to immortality we can achieve. Thank you for joining me on this cosmic journey. If you're fascinated by the mysteries of the universe and our place within it, don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep looking up and wondering about the vast wonders of the universe.